Assalamu alaikum. This presentation is on analyzing events happening at the laryngeal glottis level during a voice vibratory cycle. This would cover things like the glottal area waveform, the glottal open quotient, the contact quotient percentage, and the glottal airflow waveforms. This upper trace shows a typical glottal area waveform during phonation as obtained from an electrolaryngogram. It shows the changes in the glottal area when the vocal folds are coming closer together to close up the glottis before they start to peel away from each other to open up the glottis in the later part of the vibratory cycle before the cycle repeats itself again. The speed of such movements of the vocal folds to close and to open the glottis is not uniform. They accelerate while closing and they decelerate while opening, and these changes can be seen from the lower trace here, which is a time derivative of the glottal area waveform. When there is acceleration in the movement of the vocal folds to close the glottis, it shows a high positive peak in here. This positive peak is used to mark the start of the closing phase. And when they slow down while getting apart to open up the glottis, there will be a small dip in here, much smaller than the positive peak, and this would mark the end of the closing phase and the start of the opening phase of the vibratory cycle. So here you could see that the glottal area waveform is divided into an open phase when the vocal folds are close together and an opening phase when they are apart. These two phases can be further subdivided into a closing phase when they are attempting to close before achieving maximum closure, and an opening phase when they are getting apart from each other before achieving opening of the glottis during phonation. We'll try to add some more details in here. This is again the typical glottal area waveform. This is the real signal of a glottal area waveform, and this is a schematic glottal area waveform. This is the time derivative, how the movements of the vocal folds can accelerate and decelerate. And this is a graph of the glottal airflow during the same vibratory cycle. To this, we would add the changes in the configuration of the vocal folds during certain moments of the vibratory cycle. Starting with here in the closing phase of the vibratory cycle, it starts with the lower lips of the vocal fold medial ends moving medially to meet each other before the upper lips can follow later to close up the glottis completely. This is due to the phase difference between the lower lip and the upper lip. This would mark number 1. And we're still in the closing phase here. You would see this positive peak and the speed of the movements of the vocal folds during closure, giving the abrupt closure segment in here, this very rapid closure, and this would be marked as number 2. And then number 3 is achieved with maximum closure of the vocal folds together to close up the glottis. So this 1, 2, and 3 are the closing phase of the vocal folds. Between 3 and 4, the vocal folds would remain closed. So this is the closed phase. And then starting from 4, the vocal folds will start to peel away from each other, again with the lower ends of the vocal folds starting and the upper ends following a bit later. At one moment in here, there will be deceleration and the movements, the speed of the movements of the vocal fold. You would see how the opening up is much slower than the closing up, which is very abrupt. The opening up is very gradual and it decelerates at one point in here. This would mark number 5, and number 6 would mark the complete opening up of the vocal fold and the start of the passage of the air from the subglottis to the vocal tract. So this would mark from 4 to 6 the opening phase, and then from 6 till 1 there will be the open phase until it starts all together again. So these are a way of describing the vocal folds movement in closure and in opening up of the glottis during one vibratory cycle. Here we would see synchronized information obtained from photoglottograms showing the glottis from above, and glottal area waveform obtained from an electroglottogram, and the time derivative of the electroglottogram showing the acceleration or the deceleration of the speed of the movement of the vocal folds while closing and opening of the glottis. In the start of the closing phase, the glottis is still open. You can see some glottic area in there, but the vocal folds are starting to get closer together. And you can see from the traces here that the closing phase had not yet started, and the positive peak has not been reached yet. This positive peak would describe the abrupt closure of the vocal folds and the start of the closing phase. It would be reached in here, and this photographs there, the vocal folds have now closed the glottis. You could see this segment of rapid change in the glottal area waveform and the very high positive peak in the time derivative. And then the closed vocal folds would remain closed for some time before starting to open up again in here. This would mark probably the end of the closing phase, when there is deceleration and the movements of the vocal folds to peel apart, opening up the glottis in this frame in here. And then progressively the opening phase would continue, opening up the glottis further until the open phase is achieved here. You could see open glottis, and we are in this area of the glottal area waveform and its time derivative. This is an example of a typical glottal area waveform for modal voice in a normal person, which would show the rapid closure of the vocal folds compared with the slow opening up of the vocal folds. This rapid closure provides harmonically rich acoustic excitation of the vocal tract. On the other hand, if the glottis remains open during most of the vibratory cycle, or if the vocal folds don't meet well in the midline, there may be a non-zero level for the glottic area during the vibratory cycle. This would lead to a short closed phase, a short contact period, and a longer open phase. The air would be escaping more during the vibratory cycle, and the airflow can be rapid and cause turbulence. Another useful index that can be extracted from the glottal area waveform is the contact quotient, which reflects the duration of the time the vocal folds are in good contact in relation to the time of the whole cycle. This can be measured by having a line at the 70% from the maximum closure or 30% from the minimum closure, and at this point in time you can drop a line here to measure the time. In here, this time in relation to the whole cycle will give the contact quotient. In normal males and females, it would be somewhere between 43.8 and 46.3%. And if and this would correlate well with the vocal intensity positively. So the higher this is, the higher the vocal intensity. In things like vocal cord palsy, this contact quotient would drop to 20 something rather than 43 or 46. Contact quotient can be increased by a good level of vocal training. It can also increase in some pathologies affecting the vocal folds, like rhinx edema, for example, and in some muscle tension dysphonias when the voice is pressed. On the other hand, the contact quotient would be reduced if there is reduced contact between the vocal folds, as in vocal fold palsy or in presbylaryngeus, or in some muscle tension dysphonias associated with weak and breathy voice. What is also of importance is the standard deviation of the contact quotient between different cycles, as this would generally reflect an increase in dysphonia due to the difficulty in controlling the degree of contact from one cycle to the other. To illustrate this further, these are traces of glottal area waveforms from a patient with vocal fold palsy before and after medialization procedure. Before the medialization procedure, you could see the short closed phase and short contact quotient. The contact quotient for this patient was 28 point something compared to the usual 45 or 46% contact quotient. After the medialization procedure, things improved. The voice is now better and no longer breathy and weak. The contact quotient here has improved to 48%, and there is a longer contact period, longer closed phase, and a shorter open phase. So what are the factors that this vocal fold contact pattern depends on? Primarily the degree of the vocal fold approximation by the adductors, the glottal channel geometry, its extent, its depth, and the duration of the contact, the subglottic pressure, and the vocal fold's intrinsic stiffness during adduction. Changes in any of these parameters can influence the fundamental frequency by affecting the vocal fold contact mode. We now move to the glottal airflow waveform, which reflects changes in the airflow through the glottis during a vibratory cycle of the vocal folds. The upper trace here shows the glottal airflow during a vibratory cycle, when the airflow starts to pass through the glottis, increasing up to a maximum point and then decreasing up again before it stops altogether during the closed phase, and then a new cycle starts. It demonstrates the flow in terms of liters of air per second. The lower trace is the time derivative of the upper trace. It shows how the airflow accelerates or decelerates in time, in the corresponding time during the same vibratory cycle. So when the velocity of the airflow increases in here, it accelerates, and when the flow starts to decrease per unit time, it starts to decelerate until it reaches a point of maximum deceleration. This point is called the glottal closure instant. This is when the glottis is closed, and this starts the phase of the closed phase, which is made up of a closed phase and also a returning phase when the glottis is returning back to the baseline. The open phase, on the other hand, is also made up of two smaller sub-phases. The opening phase, when there is acceleration in the flow until it reaches a maximum, and then the closing phase when the glottis starts to close up again and the flow starts to decline until it reaches a minimum at the glottal closure instant. Here we see the glottal airflow waveform in the lower trace relative to the glottal area waveform, the size of the opening in the glottis in the middle trace. And as you can see, they generally follow each other. When the glottal opening increases, the glottal airflow increases. When it decreases, it also decreases. When it's closed, there is also no flow. So generally speaking, they follow each other, but there are some obvious differences as well. They reach a peak at different moments in time. The peak of the glottal area waveform, the maximum opening, does not correspond to the maximum airflow. You could see that the maximum airflow is shifted to the right relative to the maximum area waveform, and this is due to the inertia of the air column above the vocal folds in the vocal tract. This is an example of the interaction between the glottis as a source and the vocal tract inertia as a filter. There is also another example of this interaction between the source and the filter, in that when the area waveform is brought to the minimum, the baseline, there is still here some flow even when the area is closed, again due to the same reason of the coupling of the source and the filter during the voice production. The other thing is you would see the very gentle and slow decline of the glottal area waveform in here. In the glottal airflow, the decline in the flow at the end of the cycle is very abrupt and quick. These are the obvious differences between the glottal airflow waveform and the glottal area waveform. From the glottal airflow waveform, some ratios and measurements can be obtained, giving some useful quotients and ratios. The first group of these quotients relate to the duration of the different parts of the vibratory cycle. The duration of for example, the open phase, when the glottis is open and allows the flow to pass through it, that is formed of the opening phase in here and the closing phase in there. These two phases together constitute the open phase, and the duration of this open phase in relation to the duration of the whole cycle is the open quotient. The duration of the opening phase in relation to the closing phase, this is the two sub-phases of the open phase, the duration of the opening in relation to the duration of the closing is called the Skewness quotient or the speed quotient, and again that is of some clinical value, as we shall see. This glottal open quotient, the sum of the opening and the closing phase of the glottis open phase to the duration of the whole oscillatory cycle, determines some of the voice quality. Changes in the spectral slope are determined by this ratio. This ratio normally should be between 0.4 and 0.7. That is to say, between 40%, the open quotient should be between 40% and 70% of the whole of the glottal cycle. When it is more than 70%, when the glottis is open more than 70%, this favors more the lower harmonics, and the first harmonic will become dominant and gives a breathy voice. On the other hand, when this quotient is decreased below 40%, below 0.4, this favors the second or even the fourth harmonic, and this gives a pressed voice when the glottal open quotient is decreased below the level of 0.4. This skewness quotient, which is defined by the duration of the acceleration divided by the duration of the flow deceleration, ranges between 1.1, where the two are almost equal, the duration of the acceleration and the duration of the deceleration, to 3.4 when the opening phase is as much as 3 times the duration of the closing phase, due to the abrupt closure of the vocal folds. So the physiological range would be this 1.1 to 3.4. A higher value than this would indicate that the flow decreases very rapidly in the closing phase, which will lead to a higher vocal intensity. This is usually related to hyperfunctional dysphonia. The time taken for the vocal folds during its abrupt closure to close up the glottis is termed TA and can be calculated from the glottal flow chart and its time derivative in this time in there. This period, if it is shortened, if you have a very abrupt closure of the vocal folds, would result in a bright voice which projects well, as we have just seen. On the other hand, if there is incomplete closure of the glottis or slow vocal fold closure resulting from, say, a pathology or paralysis, this would result in less energy in the acoustic spectrum and fewer higher harmonics. This will result in a breathy voice that is not going to project well. By this, we end this presentation on events happening at the laryngeal glottis level during phonation, including the glottal area waveform, the glottal airflow waveform, and the contact quotient between the vocal folds during phonation. Assalamu alaikum.